Hello students, you all are warmly welcome to our YouTube channel Chemistry Teacher. We are going to present you another lesson belong to the very first unit. Students, so far we have discussed about the atom, the atomic theory presented by John Dalton. Then after discoveries of electron, proton, neutron, those. Then we talked about the radioactivity as well. We started talking about the atomic structure. The model represents the atom or the way those particles arrange there within the atom. We started only. So we have a long journey to go ahead. So students, we found that nowadays what we believe is the quantum model regarding the atom. But we found that out in its evolutionary stages. It was John Dalton at the very first time told that atom is like a golf ball. So you can't divide it further. But it was disproven by the discovery of the electron. Next, by J.J. Thomson. So J.J. Thomson then presented his model regarding that. It was the plum pudding model. You like plum puddings, right? It's the plum pudding model. So saying that within a positively charged sphere or globe, those electrons are immersed. So it's quite like plums in a pudding. So he presented his idea regarding that. Okay, the next model was the planetary model of Ernest Rutherford. Students, it was in 1911 Ernest Rutherford discovered the nucleus of the atom. So based on a gold foil experiment observation done by Guide and Master, his two students, under Rutherford's supervision, Rutherford, analyzing those observations, introduced or revealed that you have a nucleus within the atom. It is having all the positive charges and the mass within the atom confined into a narrow region is the nucleus. So the way you find the electrons there within the atom is those electrons are available all around that nucleus. So those electrons are orbiting, are revolving around the nucleus as those planets are revolving around the sun. That was the idea. That was the planetary model. So then after, it was found out some shortcuts, some limitations with that planetary model. So that's why the next model came. So the next model came was Niels Bohr's energy shell model. We are going to discuss about energy shell model soon in our next lesson. Students, then after, in the basis, so it's as a development of this energy shell model only, you get the current model, present model. We are calling it the quantum model regarding that. Okay students, we have got 2 lessons to come. So before that, my duty is to show you what are the background information, what was the environment when Niels Bohr was presenting his model. Students, we need to talk about electromagnetic radiations and quantum theory. So without knowing those informations, concepts, we can't go ahead with Niels Bohr's energy shell model. So those concepts affected highly on Bohr's, so as to present this idea of energy shells. So therefore, let's look at the concept electromagnetic radiation, what are electromagnetic radiations, as well as then after the quantum theory. Okay students, let's find out what electromagnetic radiations are. Electro, you have this part, electromagnetic radiations. If you have those 3 words, they are combined together in electromagnetic radiation. Students, hope you already know what the term radiation stands for. It's the traveling of energy without having an aid, a support of a medium. Then we call it the radiation. It's the radiation. So when you have energy being traveled without having any aid, support of a medium, that's what we call radiation. You then know radiation. So this radiation at the time is having a touch with electric and magnetic fields. Then only they are electromagnetic radiation. So, if I further explain this, it's when energy can travel in the form of radiation, it's you have oscillating electric field there belong to that energy, and you have oscillating magnetic field as well belong to the same, but they are not in the same direction. So the magnetic field and electric field, they are oscillating into let's say they are perpendicular to each other in two directions. Then when you consider the traveling direction of this energy, so energy can transport, energy can travel perpendicular in other direction. It's perpendicular to both of oscillating electric and magnetic field. Such a radiation is referred as an electromagnetic radiation. Okay, let me further explain that. Students, if this is the traveling direction that you have, standing for this electromagnetic radiation, let's say it's the traveling direction. So then in the Cartesian plane, you would have, if this is the x-axis, you would have a y-axis and it's perpendicular to x-axis, and you would have another axis is the z-axis. So perpendicular to both x and y. So they are perpendicular to each other. Okay. So then one is the electric field, the other is the magnetic field, but they are oscillating. Oscillating means changing their field strength as well as the phase. So let me show that. If I draw it as a sinusoidal wave, right? It's a sine shape. So if I draw it as a sinusoidal wave, so students, you would get this being having a crest, then having a trough, then again having a crest. So perpendicular to that, perpendicular to traveling direction. So this is the oscillating, let's say it's the electric field. So it's increasing field strength. It's the maximum here. Then it's decreasing. So then that's what we call oscillating, changing. Now it's changing the phase. So it's further increasing in the opposite phase. So now it's decreasing. It's oscillating. Its strength, height. So field strength is changing in a way like that. That's what we call oscillating. Then student, this is in the y-axis. In the z-axis perpendicular to that, you have got another similar sinusoidal wave. So you have oscillating magnetic field there. So then it's changing its phase. It's oscillating magnetic field, increasing. It's the maximum, so it's decreasing. This is just the way we could show it in the three-dimensional sense. So then they are perpendicular to each other. That's all. They are perpendicular to each other. So when you have such a traveling direction having oscillating electric field perpendicular to traveling direction and oscillating magnetic field perpendicular to both traveling direction and electric field, so such we call electromagnetic radiations. Then students, they are waves. These electromagnetic radiations could consider as normal waves. Okay, then these waves are like other normal waves have, this is one wave, this is one wave. So this wave's length is the wavelength. You have a wavelength standing for any wave including electromagnetic waves, radiations. Then students, we could define it as is the distance, it's the length between two crests or we are having regarding waves, if we are having the other sense, other idea, if the number of waves transported or passed a certain, let's say, place, certain, certain position at a unique time is called the frequency, or otherwise, if the number of waves produced at a unique time is called the frequency. Okay, so frequency here we denote by the Greek letter nu. So students, it's you have wavelength standing for this wave, electromagnetic wave, as well as you have a frequency. Wavelength, the standard unit or SI unit measuring wavelength is meters, is in meters. So frequency would be expressed in hertz. So its in SI unit is per second. Okay. So then, as all the other waves, these waves, electromagnetic waves, also have what? Such two terms, such two characters, properties. One is the length of the wave, is the wavelength. So it's the length between two crests or two troughs. You could measure it in that manner. So anyway, the idea is the length of the wave is the wavelength. So the number of waves produced per unit time period per second, 1 second, within 1 second, and then it's called the frequency. So it's measured in hertz or per second. Then students, there is a distance traveled by a wave within 1 second, within the unit time period, that we would take as this is the distance of one wave, and when you multiply it by the number of waves, you get the distance traveled by the wave within 1 unit time, 1 second. It's frequency into wavelength, you get the speed or the velocity. It's the distance traveled by the wave within a unit time period in a certain direction when it is velocity. So if you do not mention the direction, it's just the speed. So if we have this relationship, speed or velocity is equals to the frequency into wavelength. So regarding electromagnetic radiations, you could find there are frequencies when the wavelengths are given, wavelength when the frequencies are given. But don't you see this point? To do that, you need to know the speed or velocity. What's the speed of one particular electromagnetic wave? Students, let me reveal this thing. All the electromagnetic waves are having the same velocity in the vacuum or in the space. So it's 3 into 10 to the power 8 roughly what we say. It's 3 into 10 to the power 8 meters per second, what roughly we say. But its real value is 2.998 into 10 to the power 8 meters per second. Is the velocity, is the speed of electromagnetic waves. All the electromagnetic waves in space. When you have no medium, then it's this in vacuum. So students, how do you see this point? If you have seen this value somewhere else as well, where is that? 3 into 10 to the power 8 is the speed of light. Then it says that the light itself is also a type of electromagnetic radiation. Okay, so you have various types of electromagnetic radiations. How could it be possible? Students, it's when you have the same speed standing for all the electromagnetic radiations, but when you have speed being equals to frequency into wavelength, then if you could find various frequencies and various wavelengths, but their product always is the same. So then vary their wavelengths as well as frequencies. If you could find various different types of electromagnetic waves, radiations. Then what are the such radiations? Students, it's you could find radio waves, it's you could find microwaves, you could find infrared, you could find visible light, you could find ultraviolet, you could find X-rays, you could find gamma radiations. It's such electromagnetic radiations are there, been available, varying their frequencies, therefore wavelengths. So it's you would be kind of provided with some details, some information, data, let's say, as to reveal some such terms. Let me show you in an example. If it is you are provided with in a question, if you are provided with some wavelength information data as the wavelength of specific electromagnetic wave with this color, right? Let's say it's a colored electromagnetic wave that lies within the visible region. So it's you get 600 nanometers. It's they are saying, let's assume, it's they are saying the wavelength of particular electromagnetic radiation is 600 nanometers. Then what is the frequency? What is the frequency of that? Saying, giving that information, they are asking for the frequency. Students, then it's we need to apply the equation. Equation is the velocity or speed equals nu lambda. So nu is the frequency and lambda is the wavelength. Okay, let's substitute values here. It's the velocity of electromagnetic radiations is 3 into 10 to the power 8 meters per second. We all need to know that. Then students, it's what we are going to find out is the nu, is the frequency. Then we could substitute the lambda, the wavelength value being given, but it's in the units of nanometers. You need to convert that into SI unit, meters. So the way you could convert nanometers into meters is multiplying that by 10 to the power minus 9. Then you could transform into meters. So this is the value. So students, it's you could find it out as its frequency equals, this becomes 6 into 10 to the power minus 7. They are at that side. So it is 6 goes there and become half. Half means 0.5. Let's say 5 into 10 to the power. Then this is plus 7. This is 10 to the power minus 7 comes here, makes it 10 to the power 14. So that's it. The answer. Students, in that way, 14 per second. That's it, the answer. In that way, you could find it out. When the wavelength is given, you could find out the frequency. Other way also you could do. Let me show you another example. Students, if they provide you the frequency of a particular wave, as let's say the frequency of a wave is 2 into 10 to the power 15 hertz. So then what's the wavelength of this particular electromagnetic radiation? If we are about to find out the wavelength using the given frequency of electromagnetic radiation, students, let's substitute it in the equation. C equals nu lambda. C is the velocity. So it's the same, the velocity of all the electromagnetic radiations. It's 3 into 10 to the power 8 meters per second. Then students, the frequency here, according to this example being given, it has to be in the units, SI units. So we need to convert this hertz into SI unit. It's per second. So it's they are the same. When you have 1 hertz, it is 1 per second. So it is 2 into 10 to the power 15 per second is the units now. Then students, it's you have lambda to be found out. Lambda is the wavelength. It is 1.5 into 10 to the power 1. This plus 15 comes here and becomes minus 50. So students, it's 10 to the power minus 7 it becomes in meters. Further, in nanometers, if you represent the same, it is 10 to the power minus 10 to the power, you could say plus 2. multiplying this 10 to the power minus 7, 1.5 into 10 to the power plus 9, it's the nanometers, so it is 150 nanometers. In that way, you could find out the wavelength when the frequency is given and frequency when the wavelength is given. Anyway, you could use this equation. This equation shows that it's the same velocity at all the times what you get. Then if the same velocity, this product, its frequency to wavelength product would be a constant. Then to keep it, maintain it constant, if you find the frequency being low, then its lambda, the wavelength, going to go high, going to be bigger in value. Other way also it's possible. If your wavelength is low value, then the frequency will be maintained as it's giving the same constants till the product. So the frequency will be high. So therefore, for high frequencies you could expect lower wavelength. For lower frequencies you would expect high wavelengths. So therefore, you get a variety of these electromagnetic radiations. Within these all the electromagnetic radiations, it's a variety you get based on their frequency, or you could call it based on their wavelength. So they would have different wavelengths. They would have different frequencies. Therefore, there would be different electromagnetic radiations. It's when you get one set having close frequencies, or let's say close wavelengths, you would find those being named as in one particular way, as let's say it's a visible light, also a type of electromagnetic radiation. But students, when you pass this visible light through a prism, you get 7 major different colors but many sub-colors as well. So then it's this visible light, white light, it consists of various different colors. So it's various different therefore frequencies, but they have close values. So within a certain region, you get all the frequencies possible to be there. If you get such, we call an electromagnetic spectrum. Electromagnetic spectrum. Again, you could have various electromagnetic radiations with various different frequencies as well as wavelengths. Then if you arrange those frequencies in the ascending or descending order, in an order, if you get all the frequencies belong to a certain set means within a given region, means within a given range. If you find all the possible frequencies or all the possible wavelengths, means all the possible wave they are found present, then such a set is identified as the electromagnetic spectrum. Then students, when you arrange all the waves in their ascending order of frequencies or in their ascending order of wavelengths, then what you get is this electromagnetic spectrum. So you would find all the varieties there within that range, given specific range. Okay, so if we follow the direction as, let's say it is the direction where frequency increasing direction, then in this direction, if frequency increases, then in the same direction, lambda means the wavelength would get decreased. So then you would find the greatest lambda wavelength with radio waves. Radio waves. Then students, it's the least in frequency. Then what you get next is microwaves. Microwaves having greater frequency than radio waves. Then further it is infrared. Then next is the visible light. Next is ultraviolet. Next is X-rays. Next is gamma rays. in that manner, you could find those electromagnetic radiations arranged in an order in the increasing order of their frequency, in the decreasing order of their wavelengths. So, if you follow the other direction, it's the decreasing order of their frequencies, it's the increasing order of their wavelengths. For the reason, it's always frequency into wavelength is the same constant velocity standing for those electromagnetic radiation is 3 into 10 to the power 8 meters per second. Meters per second. Okay. Then students, we have what enough regarding this electromagnetic radiation. Our next topic is quantum theory. So let's look at this topic, quantum theory now. It was in year 1900, the scientist named Max Planck presented this idea for the very first time. What's the quantum theory? When those matters, they emit radiations, let's say any hot body is emitting radiation, or any cold gas or something absorbing radiation. When it is an exchange of radiations, when you have those hot matters, they emit radiations, and when you have some cold matters, when they absorb radiations, it's anyway exchanging of radiations. So when it happens through electromagnetic radiations, it's either they emit electromagnetic radiation or they absorb electromagnetic radiation at this moment, at this context. So then when it is doing in that manner, those energies would be exchanged in discrete quantities. It's not a continuous quantity, it's a discrete quantity. Discrete means some limited amounts like packet-wise, portion-wise, they do that. So there is the smallest unit within those energies, electromagnetic radiation energy. It's like when you find the smallest unit atom within matters there, it should find these smallest portion, these smallest energy amount within energy with electromagnetic radiation. This smallest energy amount was called as an energy packet, a quanta. So energy is fractionated or fragmented into quanta, means it exists, get emitted as discrete amounts, as of energy packets, as of quantas. So this is called the quantization of energy. Okay, this is the fundamental in quantum theory. Students, when those hot bodies, they emit electromagnetic radiation, or when those cold gases, they absorb electromagnetic radiation, it happens via small portions, quantas of those energies, energy packets of those energy. Let's assume that this is a hot body. It's emitting radiation, electromagnetic radiation. Let's say it's a hot filament. It's emitting light. It's emitting electromagnetic radiation in a direction somewhere, all around actually. So students, when you check for those electromagnetic radiation, if you could find them packet-wise, there would be a smallest unit, smallest amount of those energy. So unless in the form as of these smallest energy amount, as let's say energy packets, they would not emit energy. If you could get one packet being emitted, or two packets, three packets, four packets, 5, 100, 1,000, million, billion, such packets, many such packets you could get. So then, if you won't ever get such many packets and a piece of a packet, half of a packet, quarter of a packet, you won't ever get a fraction value there. That's the point. It's only done via multiples of packets. It's either one packet or many packets. If you have this got find lesser than this packet, it would never emit that energy. That's the idea. That's the idea of quantization of energy. So when this energy emission is done via energy packets in a discrete amount of energy. So they absorb also. When they absorb also, it happens in the same manner. So students, when they take energy in, it's done via quantas. It's done via energy packets. That's the idea of quantum theory. So it's Max Planck first presented that, and Max Planck further said any electromagnetic radiation is having its own specific frequency. Okay. So these energy amounts, the minimal energy amount, the energy packets energy amount, quantas energy amount would be directly proportional to that particular frequency. Let's say that quantas energy amount, energy packets energy amount is delta E. It's the energy. So students, it's a very small energy amount. That's why I use delta. It's the energy. Then it could be directly proportional to its frequency. That's why the relationship he showed on us. So then using that relationship, if we could derive this equation using a constant for proportionality, it's HVUs into nu. This H is called the Planck's constant. Student, it's the Planck constant. It takes the value of 6.626 into 10 to the power 1 minus 30 for joule seconds. So then, if you know any electromagnetic radiation's frequency emitted, you would find it out the smallest energy amount standing for that. What you need to do is just substitute the frequency here. You know already what the Planck's constant is. So you would get the energy in joules. Then students, it's, as we know, for electromagnetic radiations, it's C equals nu lambda. So nu equals C divided by lambda. Therefore, if we could substitute here for nu and get delta E being equals Hc divided by lambda. So if you could use either this or this. So any equation you could use when you are provided with the what? Lambda. Lambda is the wavelength of that specific electromagnetic radiation. So then, if you already know what's the velocity of all the electromagnetic radiation is the same. So it's 3 to 10 to the power 8 meters per second. So substituting those two with the Planck's constant 6.626 into 10 to the power minus 34, you would get the minimal energy amount, means the energy packets energy amount. So it could be through such energy amounts other than fractions. It's never they emit energy amounts being lesser than of such packets. It's always as through multiples of those energy packets. They do that. Okay students, that's the basic of Max Planck's quantum theory. We need to know these two equations. It's the smallest energy amount standing for an energy packet or quanta could be given as delta E equals Planck constant into frequency, or otherwise equals to Planck's constant into velocity of those electromagnetic radiations divided by the wavelength. So then let's find it out. How could we use these equations in applications? So let's talk about few examples standing for the smallest energy amount of quantum energy packet, that when those hot bodies emit electromagnetic radiations as discrete energy amounts, or when some such cold gases or such absorb those electromagnetic radiations as discrete energy amounts. It's always, according to Max Planck, what he told was discrete energy amount. Certain fixed energy amounts, fixed energy packets, they always either absorb or emit. It's other than that, you don't get pieces or parts, fractions of such amounts. Okay, so let's find it out some example questions that you could find out regarding this. Students, it's when you are provided with a certain frequency asking for the smallest energy amount of a quanta. It's we could find it out as if the frequency is given, let's say the frequency is given as 1 into 10 to the power 14 hertz. Then if you are going to find it out, the smallest energy amount within an energy packet. So then it is delta E equals h nu. So h is the Planck constant. In question papers, it's provided to you. You don't need to memorize that. It's anyway 6.626 into 10 to the power what? 34 minus 34 joules per joules seconds, not per second. So students, it's the frequency you would get be provided as 1 into 10 to the power 14. It's per second. So what you get, the answer finally is in joules. So it is 6.626 into 10 to the power minus 20 joules. Joules is the smallest energy amount that represents this frequency. The energy packet's energy amount that represents this frequency. So if you are provided with not frequency but a wavelength, so how would you find that out? Okay, let me show you that as well. Let's say you are provided with a wavelength as lambda equals 300 nanometers. 300 nanometers. Asking you to find out the smallest energy amount within an energy packet. So students, it's you would do that using that smallest energy amount equals hc over lambda. H is 6.626 is the Planck's constant into 10 to the power minus 34 joule seconds into now the c is the velocity of electromagnetic radiation. It is 3 into 10 to the power 8 meters per second divided by lambda is 300 in nanometers, but in meters is 10 to the power minus 9 meters. Then solving this it's you could easily get the answer. Students, you could find that out. When you solve that, it's 300 would become 3 into 10 to the power minus 7. 3 to 3 would cancel off. So then it is 6.626 into 10 to the power, here minus 7, here plus 8. So it goes up and becomes 15 plus 15. So when you deduct 15, it is plus 15, this is minus 34. That's why by 34 it is minus 90. It is in the units of joules what you get finally. In that manner, when you provided with either the frequency or the wavelength of a certain electromagnetic radiation, you could easily find it out the smallest energy amount, minimal energy amount found within what? Within an energy packet. So apply this. Anyway, if you are provided with any energy amount, let's say that as if you are provided with naming, this is the energy amount standing for energy packet. So let's say it is 3.313 into 10 to the power minus 20 joules, the minimal energy amount that you find within an energy packet of a certain electromagnetic radiation that emitted. So if they ask us to find out, calculate the frequency standing for that electromagnetic radiation, you could easily do that, substituting the value there in delta E equals h nu. So if you already know the given value of energy could be substituted here as 3.313 into 10 to the power minus 20 joules is the minimal energy amount within one energy packet. Then students, you already know the Planck's constant, it is 6.626 into 10 to the power minus 34 joules second. Then it's the frequency we are about to find out. So you could find that out frequency equals, so when this comes here it becomes half, so it's 0.5 into 10 to the power minus 40 plus 14. So we could further say for 13 per second. Okay, in that manner, you would find out when the frequency is asked for giving the energy amount, the minimal energy amount within one energy packet. So it's further you could find even the wavelength as well. Students, that's how you would deal with these terms. So these are few just example applications. So you could find this kind of sums being given, questions being given in your paper. So these are very simple few points that you would find, you would understand easily. Okay, so if we have come to the end here with this lesson, so students, our next topic is talking about the Bose energy shell model. So you get ready, if you are going to meet you, they are talking about the Bose energy shell model. Okay students, goodbye.